Hello and welcome to G Fun Facts Online. Today we're taking a journey back in time. Not just hundreds of years or even millions, but billions of years to a time when our planet was a chaotic, molten nightmare. We're asking a fundamental question. When did the Earth we recognize actually begin? For decades, scientists thought they had a key, a chemical clue hidden in ancient rocks that could pinpoint the exact moment our continents started to form and dance in the slow, grand ballet of plate tectonics. But what if that clue, that geological fingerprint, was telling a story far, far older than anyone ever imagined? For a long time, the story of the continents hinged on a metallic element called niobium. Here's the puzzle. The crust that makes up our continents is consistently low on niobium, while the crust under our oceans has plenty of it. Scientists called this the negative niobium anomaly and saw it as a smoking gun for plate tectonics. The theory was that when one tectonic plate dives under another in a subduction zone, certain minerals that love to hold on to niobium get left behind deep in the mantle. This means the magma that rises to form new continents is niobium-poor. So the logic was simple. Find the oldest rocks with this missing niobium signature, and you've found the birthday of plate tectonics. But this hunt led to a dead end. Different rocks told different stories, with dates all over the geological map. The clue was confusing, and it was time to ask a new question. And that new question led to a groundbreaking answer. Recent research, including a major study published in the journal Nature, has completely flipped the script. It suggests the chemical signature of our continents wasn't created by plate tectonics at all. It was there from the very beginning. The evidence points to Earth's very first crust, a quote, protocrust that formed about 4.5 billion years ago. Think about the early Earth, a Hadean eon world covered not in water, but in a global ocean of molten rock. As this magma ocean cooled, our planet's first crust began to solidify. Here's the crucial part. In the super-hot, low-oxygen environment of early Earth, niobium behaved differently. It became iron-loving. So as Earth's dense iron core formed, it acted like a giant magnet, pulling most of the planet's niobium down into the center. The mantle left behind was niobium-poor, and the first crust that formed from it inherited that trait. The missing niobium isn't a sign of tectonics. It's a birthmark from the day the Earth's core was born. So if this protocrust already had the chemical signature, what happened next? Well, it wasn't the stable land we know today. For hundreds of millions of years, this early crust was pulverized by a relentless storm of meteorites during the late heavy bombardment. These colossal impacts, along with other processes, fractured, churned, and refined the protocrust, making it richer in silica, the stuff of continents. Fragments of this crust thickened and stabilized, becoming the seeds for the first proto-continents. As these drifted apart, magma welled up in the gaps, creating something more like our modern oceanic crust. Plate tectonics would eventually take over, but the fundamental chemical blueprint of our continents was already set in stone. Now you might be wondering, how can we possibly know this if none of that 4.5 billion-year-old crust is left? The answer lies in tiny, nearly indestructible time capsules, zircon crystals. Geologists have found zircons in Australia that are up to 4.4 billion years old. These ancient messengers confirm that an early, solid, silica-rich crust existed. They, along with the oldest rocks we can find, paint a picture of an early Earth dominated not by plate tectonics, but by plume tectonics, where massive plumes of hot rock rose from the mantle to shape the surface from below. The modern style of plate tectonics, with its massive mountain ranges, seems to have kicked off much later, maybe around 2 billion years ago. This new understanding is a profound shift in Earth's biography. It tells us that continents are not just a consequence of plate tectonics, but a primary feature of our planet's formation. That chemical clue we followed for so long wasn't a footprint from the start of a journey. It was an echo from our planet's fiery birth. This changes how we read Earth's deep history and could even reshape our search for life on other rocky worlds. The story of our planet is one of constant discovery, where each new chapter reveals just how magnificent and complex our home truly is. Thanks for listening to G Fun Facts Online.